In this section, we will be working with relations and functions. Now, the definitions of these terms are given at the top of your page, and these are two definitions that you really do need to know. You need to remember these. A relation is any set of input-output ordered pairs. A function is a special type of relation in which every input value is paired with exactly one output value. Now you may want to circle or underline these words on your paper. Every input has exactly one output. That is what makes a function. So moving down to example one way of representing a function is by a table of values. So here we have three relations listed here, and we need to decide whether or not they are also functions. So looking at this first one, we have the set of inputs given on the left-hand side in the left column. The inputs are 1, 2, 3, and 4. The corresponding outputs all are 5s. And we need to decide if this represents a function. So looking at this, when the input is 1, the output is 5, and only 5. When the input is 2, the output is 5. When the input is 3, we have a 5. When the input is 4, we have a 5. For each of these inputs, there is one and only one output value. So yes, this first table represents a function. Looking at this next one, we have the input of 1 maps to the output of 8, input of 2 to -9, an input of 3 to 7, and an input of 3 to 12. Now here we're going to have a problem. If you have an input of 3, an input of 3 corresponds to two different output values. Here we have an input value with two different output values. So this relation is not a function. Looking at the third table here, we have an input of 2 maps to 4, an input of 1 to -5, 4 to 10, and -3 to -87. For each of these input values, there is one and only one output value. So yes, the third table is a function. Remember, you're looking for the case where every input has exactly one output. Now in example 2, we have ordered pairs. A function can be represented as simply a set of ordered pairs. And here we need to decide whether these relations are functions. So looking at A, we have the ordered pairs 0, -2, 1, 4, -3, 3, and 5, 0. Now if it helps just to visualize this relation, you can always put these ordered pairs into a table of values. I'm just going to have the left-hand column be the inputs again, the right-hand column be the outputs. So the first ordered pair, we have an input of 0, an output of -2, then an input of 1, an output of 4, an input of -3, an output of 3, an input of 5, an output of 0. If you look at these, every input value has exactly one output value. So A is a function. Doing the same for B, we have -4, 0, 2, -3, and 2, -5. So I'm going to draw another table here. Here's the input column, here's the output column. And writing our ordered pairs down here, we have -4 goes to 0, 2 goes to -3, 2 goes to -5. And here we can see a problem. An input of 2 has two different output values. So this is not going to be a function. Back over here in our ordered pairs, we have the ordered pair 2, -3 and 2, -5. Two ordered pairs, the same input value but two different output values. So B is not a function. Looking at C, we have negative 5, 1, 2, 1, negative 3, 1, and 0, 1. Now, if it helps, you can go ahead and draw out a table of values to visualize this relation. But looking through here, an input of negative 5 has an output of 1, an input of 2 has an output of 1, an input of negative 3 has an output of 1, and an input of 0 has an output of 1. So every input has exactly one output value. So C is a function. Doing the same with D, we have an input of 3 with an output of negative 4, an input of 3 with an output of negative 2, an input of 0 with an output of 1, an input of 2 with an output of negative 1. Again, we see a problem. Here we have an input value with two different output values. So this first ordered pair, the input of 3 has an output of negative 4. In this one, the same input, the input of 3 has a different output, in this case a negative 2. So D is not a function. Now E is a tricky one. Here in E we have only one point, one ordered pair, 1, 3. Now in order to be a function, every input has to have exactly one output value, and this is in fact the case here. The input of 1 has one and only one output value, happens to be 3, so E is technically a function. Now in example 3, the instructions say on the graphs below, plot the points for A, B, C, and D above. So I'm going to take a few minutes and just plot these ordered pairs. For A, we have the ordered pairs 0, negative 2, 1, 4, that would be about right here, negative 3, 3, and 5, 0. For B, we have negative 4, 0, 2, negative 3, and 2, negative 5. Now the instructions say to circle the problem points. So remember in B, these 2 points were the problem points. These 2 points had the same input value but different output values. So these are the ones we want to circle here. Moving on to C, we have negative 5, 1, 2, 1, negative 3, 1, and 0, 1. For D, we have 3, negative 4. That'll be about right here. 3, negative 2, 0, 1, and 2, negative 1. And this was not a function, so we're going to circle the problem points here. Now what you're going to notice on the graph of a relation that is not a function. Remember, a function, every input value has exactly one output value. So if it's not a function, you will have the same input mapping to multiple outputs. Graphically, what you'll see is 2 or more points that fall on the same vertical line. If 2 points have the same input value, then on a graph they're going to be right above each other. They will have the same input value. This is the reasoning behind what we call the vertical line test. The vertical line test says if all vertical lines intersect the graph of a function at only one point, then the relation is a function. You never have the case where one input has multiple outputs. If, however, a vertical line intersects more than one point at once, then you have the case where a single input does have multiple outputs and it is not a function. So that is the vertical line test. That is what you have to remember. So example 4 has some graphs and you need to use the vertical line test to determine which of them are functions. So what you need to do is imagine passing a vertical line through the entire graph and see if it ever hits more than one point at a time. So this first one we have is a circle. I'm just going to imagine passing a vertical line right here. And immediately you see that there's a problem. We hit more than one point at the same time. This would happen if we did the vertical line over here or at any other spot on the graph. All right, if at any time the vertical line hits more than one point at once, then it's not a function. So this one, this first one, this circle, is not a function. We have the case where a single input has more than one output. Looking at the second graph, if you imagine passing a vertical line through here, as we go along through the function, you will never have a time when a vertical line hits more than one point at once. So this second graph is a function. The third one, we run into a lot of problems. Imagine passing a vertical line right here. It hits multiple times. So this one definitely is not a function. The last one here, we have just a set of points and the same trick. You just want to pass a vertical line through the entire graph and just make sure that it never hits more than one point at a time. So in this case, yes, this one is a function. Now when you're dealing with the graphs of functions, the graphs of functions will either be increasing, decreasing, or constant. This is what we call the behavior of graphs. Increasing functions will generally rise as you move from left to right. As the input values increase, so do the outputs. So this could happen at a constant rate. Here I'm just drawing an increasing line. And they could also have changing rates. What you're looking for is just that. As the input increases, so does the output. So the graph will rise to the right. If a function is decreasing, as the input gets larger, the outputs get smaller. So the graph will fall to the right. So here we have a decreasing function that's decreasing at a constant rate. And it can also be curved. Let me draw a couple more examples here. But in general, a decreasing function falls to the right. Now the last case is a constant function, and there's only one example of this. A constant function is one in which, as the inputs increase or decrease, the outputs stay constant. They remain exactly the same. And so the graph will be a straight horizontal line.